Hello. Thank you for taking the time to tune in to the latest in our series of CDSG webcasts. Today we'll be discussing PCIe compliance testing for NVMe removable storage, featuring subject matter expertise from our own engineering team, as well as from Granite River Labs. My name is Chris Kruhl. I am the Director of Marketing at the CRU Data Security Group, the parent company of the CRU removable storage brand, which includes the recently announced SHIPS platform. CRU has been entrusted to secure sensitive data for over 30 years with our removable storage devices. You'll find our products in the hands of well-known organizations and government agencies all around the world. And Granite River Labs provides test services to help hardware developers implement high-speed connectivity technologies as these technologies become faster and more complex and harder and more difficult to test. GRL has worked with over 500 semiconductor and system companies, providing end-to-end engineering services and test solutions from their worldwide test facilities and R&D centers. Before I introduce our guests, I'd like to cover a few housekeeping items. Everyone except our presenters will be muted throughout the session. You will have the opportunity to post questions throughout the webinar. You'll find a question and answer section on the right-hand portion of your streaming window. We will address as many questions as time allows at the end of the presentation. And at the end of today's session, we will announce our next CDSG webinar topic. And our last housekeeping item is to let you know that we will send out a survey after the webinar as we welcome your feedback. Today, Stuart Lowe from the CDSG engineering team will be showing us a few products from the SHIPS platform lineup. Stuart has been designing CRU products for over 15 years. And as part of his process, we submit our products through endurance and thermal testing, as well as PCIe compliance to ensure the longevity of your CRU removable systems. Stuart will demonstrate the SHIPS products in a few of our endurance tests before Eugene dives deeper into Granite River's PCIe compliance process as it pertains to CDSG products. Eugene has worked in semiconductor capital equipment, aerospace, medical, and consumer electronics. I'm sorry, that is Stuart. Stuart spends his time, he has worked in semiconductor capital equipment, aerospace, medical, and consumer electronics. Stick to the script, Chris. He spends his spare time remodeling one house or another, playing with the grandkids, teaching Sunday school, and mowing the lawn. And after Stuart's presentation, we're pleased to feature Eugene Sushansky of Granite River Labs. Eugene is Director of Global Engineering at GRL headquarters in Santa Clara, California, where he manages all technical aspects of GRL's global testing activities and represents GRL on the PCI SIG and other standards groups. Prior to GRL, Eugene spent over 2 years at Toshiba America Electronic Components, TAEC, where he was Senior Hardware Engineering Validation Manager, and over 13 years at PLX Technology, now Broadcom, as Senior Design Manager. Eugene is an expert in silicon and discrete component characterization, as well as SerDes and discrete components validation. He has extensive expertise in electrical characterization of PCI Express, SAS, SATA, and other high-speed data standards. Eugene will today talk about how they do PCIe compliance testing and the importance of PCIe compliance for product reliability. At this point, without further ado, I'll turn it over to Stuart.
Well, good morning. I'm Stuart. I'm one of the engineers at CDSG working on the SHIPS platform. As Chris didn't mention it, secure high-performance storage platform. I'm going to give a quick overview of some of the mechanical portions of the SHIPS and some of the testing we've done. The heart of the SHIPS platform is the cartridge itself. It's quite small. The module, the cartridge has an aluminum extrusion for mechanical portions, but it also acts as a heat sink. And then inside we use thermal interface material, and we have a temperature sensor in order to control the temperature of it. One of the key elements in the key design efforts was this little connector on the end. I hope you're in focus there. Doesn't look like very much, but in order to get the high speed out of it, the durability and make it a cost-effective connector. A great deal of effort went into that. Size, of course, was one of the limiting factors. We had to have a pretty small connector. The ship's platform consists of several components, or optional components. This happens to be the QX448. It retains 4 of these cartridges. It is lockable, and it has 4 little doors here. They cam out. One of the features of the this connector system is it is vibration resistant and highly durable, which also means it has pretty high demate forces. The door acts as a cam or a crowbar, if you happen to be a carpenter, to open the doors. The product itself connects to the host through 4 separate cables, 1 per bay, mating to a CDSG host bus adapter, because most motherboards don't have 4 PCIe ports that we can cable out on. And we can control up to 3,200 megabytes per second off of this product, which is the theoretical limit for 4 lanes of PCIe. Another product that we have on the market today is the QX118. It is a 9mm optical disk drive form factor. This was actually the target volume, kind of the least common denominator volume that drove this size. Yeah, the same door concept anyway, pries out, also capable of 3,200 megabytes per second. We're going to jump to some reliability testing we've done. One of the other key design requirements was a high mate demate life. As Chris mentioned, we've been in many markets for many, many years, and longevity is one of the key factors. We go into products that are demated 2, 3, 4 times a day, and for 5 years at a time. So we're talking about thousands of cycles. The connector system has to be extremely robust. This particular video that's being shown right at the moment is a mate demate system. We're exercising the push button, the catch, the door cam, and the docking connector, which is the single most critical portion of it. Previous test samples, we've run up to 120,000 cycles. And this particular one that we see in the video here has 50,000 cycles on it. Next slide is going to show some photographs, some thermal images of what we've done for thermal management. M.2s, you look at the specs and they're running 6 or 8 watts, not that big a deal, but when you realize that it's coming off of such an extremely small surface area, the power density is very high, and so they tend to run extremely hot. The photograph on the left there shows you what unmanaged thermal properties are like. It's ran up to 65 degrees C in less than 3 minutes after running a streamed read-only. The M.2 modules begin to throttle their speed when they get up to about 65 or 70 degrees C. So this particular sample has already begun throttling. So it started out at 3,200 megabytes per second, and it'll go down to 27, or I've seen it go down to much less than 20 megabytes per second, trying to maintain that heat, trying to keep the product from overheating. The module on the right, or the photograph of the module on the right there, is the exact same test bed, the same model of M.2 running the exact same test load. After 5 minutes, it was up to 32C and never got over 32C after a 30-minute run. And that's how we manage the thermal of that, is what provides the maintained high data rates of 3,200 megabytes per second. So currently in production, we have what we call the QX80, which is this cartridge right here. The QX448, which is the 4-bay version, and the QX118, the single bay version. But we made the product as flexible as possible so that it could go into various platforms. OEMs are discussing other custom platforms with us even now. And we have currently in development a mill-grade module that will take even more power and have better thermal management than this. And our next up is our guest speaker from Granite River Labs.
All right. Good morning, and thank you for the introduction, Stuart. So my name is Eugene Sushansky, and I'm a Global Director of Engineering at Granite River Labs, headquarters in Santa Clara, California, Silicon Valley. So today I'll be talking about how we do some of the PCI Express testing, and I'll be concentrating primarily on the electrical side of that testing. I will touch up on Gen 3, which is 8 giga transfers per second, going to Gen 4, which is 16 giga transfers per second, and I'll mention about something Gen 5, which is 32 giga transfers per second. There is a Gen 6 as well, which I'll slightly touch up on, but won't be given any much of the details. Okay, so next slide. Okay, so today's agenda, as I already mentioned, I'll be talking about the evolution of PCI Express, the topologies that PCI Express defines, the special interest group defines between base and a CAM. I will go over the overview for the transmitter testing, then Gen 3, Gen 4 receiver testing that will include the receiver compliance, receiver link equalization testing, and touch up on transmitter link equalization response time testing that we have to do. And after that, we will have a small Q&A. In my presentation, I will have short videos that due to the time constraints, we may have to limit some of the duration of the video, but they're going to be fully available on a slide as you guys gonna download it after the presentation is over, the webinar is over. So going to the next slide. So just a little bit of a history. So who is JRL? So we have been founded in 2010, Silicon Valley headquarters, and currently we have 8 labs around the world. So anywhere you go, you're gonna find JRL and the expertise that we provide. So what do we do? We provide testing services and automation solution for the connectivity and charging type of testing. So JRL supports PCI Express ecosystem, and we do support a lot of other standards. But given the fact that we are going to be concentrating on PCI Express, that's what we're going to look into today. Next slide, please. So the PCI Express evolution. Next slide. Okay, so historically, everyone demands things to go faster. Software engineers complain that hardware is too slow, and hardware engineers complain that software algorithms takes too long to process or load certain things. So regardless, everyone desired to have one unique interconnect for speed and interoperability. Back in the beginning of 2000s, the 3GIO specification, which later got renamed to PCI Express, was born. In today's date and age, PCI Express is considered to be one of the main interconnect standards. It exists in almost every computer architecture and enables infinite amount of applications to be run on. So as you can see, we have artificial intelligence, we have automotive, which is actually very popular today. We have iCloud, enterprise storages, mobile, as well as just regular storage devices. Next slide, please. Okay, so PCI Express has started at 2.5 giga transfers per second, which was named as Gen 1. With a growing demand and a bandwidth, it actually doubled in average of 3 years. So today we are working on Gen 5, which is 32 giga transfers per second. And we're already actually looking into the Gen 6, which is 64 giga transfers per second. Next slide, please. So the initial Gen 1, which is 2.5 giga transfers per second PCI Express, has followed the NRZ type of modulation. That concept prevails up to Gen 5, 32 gigatransfers per second. Starting with the PCI Express Gen 6, which is 64 gigatransfers per second, the PAM4 modulation is adopted. The 8B, 10B encoding was only used with Gen 1 and Gen 2. With Gen 3 and going forward, 128B, 132B encoding was adopted. This was done to sustain the throughput and overall data integrity. Another addition that to the Gen 6, the PCI Express has introduced the FEC, which is a forward error correction. We'll talk more about it later on in the slides about each and every specification for the electrical testing. Next slide, please. Okay, so PCI Express has two different topologies. There's a base specification and card electromechanical specification, which is abbreviated as a CEM, C-E-M. So for base specification, there is no real official compliance testing that you can perform or do, but you still need to be able to test your silicon or whatever design you're working on. So there is no official fixtures for PCI SIG, but you can actually develop an evaluation board to do the testing. So for the CEM specification, that is actually the compliance is actually clearly defined. It provides the fixtures from the PCI SIG that are tuned and correctly designed for every channel there is for each and every data transfer that PCI Express supports. So those test fixtures are available from the PCI SIG to be purchased for non-members and members as well. There's also M.2 and U.2 specification that are subform of the specification for the card electrical specification. Next slide, please. Okay, so one can say that base and CEM specifications are similar, but in reality, they're not. The measurements in the base specification are done at different test points between CEM and the base. So different tools and methodologies are also used, and the coverage are different too. So for the base specification, the evaluation board needs to be designed in order to be able to do any type of testing. So all of the testing for the base specifications are done at the package balls of the silicon under test. Also for the back-end processing, the CSIM tool is used for receiver and calibration. Now looking at the CEM electrical specification, like I already mentioned, the official test fixtures are defined and available for customers to use. The post-processing tool that is used, it's actually PCI SIG test tool developed by Intel. Next slide, please. So what's important right now is a lot of vendors vendors coming to our door and saying, well, I have something, what should I test it for? Well, one thing I can tell you is if you are an ASIC vendor and you're selling an ASIC for different type of application, you always want to verify and test your silicon to the base specification. Base specification is clearly defined, but you do require to provide an evaluation board to be able to test it. There's different aspects of embedding and de-embedding different traces in order to do the measurements, but overall, the spec clearly defines what your signal supposed to look like. If you have an end product that is going to be used and sold off the shelf for various consumers or maybe enterprise customers, then you need to test your product to card electromechanical specification. The key is that it needs to comply in order for you to be entered into the integrators list by the PCI SIG committee. Now, there is a little caveat. So if your ASIC is going to be, if you're an ASIC company and your ASIC is going to be designed to one specific application, then you can claim that I would like to test it to the card electromechanical specification. But like I said, if you're planning on using it in multiple applications that are not clearly defined by your end user, then you are required to test to the base specification. So next slide, please. Okay, so let me touch up on the transmitter test overview. Next slide, please. So the evaluation test board is required for testing to the base specification, as I already mentioned. So a replica channel is measured and embedded during the TX testing in order to make sure that we bring the test points to the balls of the measurements of the ASIC that you're after. So with the for the base specification, you can actually test transmitter for the electrical characteristics. You can test presets if you're Gen 3 and any future generation of the PCI Express specification. You can test presets. Those presets are clearly defined to be from P0 to P10, and you can also test PLL, and it's all can be done on the evaluation board. Next one. Next slide, please. So this would be just a general representation how transmitter testing is done. You have an evaluation board, you have a silicon, you have a ref clock going into that silicon, and you have that breakout channel connected to the scope via cables. Depends on the scope vendor you use. It could be channel 1 and channel 3 or channel 1, channel 2. The replica channel, like I said, this is something that gets measured and de-embedded during the measurement in order to bring the test point up to the balls of the silicon. Next slide, please. Okay, so as already mentioned for the PCI SIG, there's actually test fixtures provided, and as you can see, they're on a kind of in the middle right side, and on the next slide, we're gonna have a zoom in of those fixtures so we can check. So those test fixtures are Gen 4 fixtures. I didn't actually show the Gen 3, but during our video, you're gonna see how Gen 3 fixtures look like. So you can see that test fixture actually consists of 2 CLB boards. It's the first picture, right, kind of towards the center of the slide. One of them is by 1 and by 16 type of topology, and the second one is by 4 by 8. Right in the middle, the picture is the CBB, stands for compliance base board. This is where the ref clock is and all of the transmitter and receiver points are. And the one on the right is actually an ISI channel. So for Gen 3, the ISI channel is clearly defined and is present on a fixture. For Gen 4 and going forward, the ISI channel is different. The reason why PCI SIG decided to do that, because during manufacturing, it's very hard to control the ISI and to be exact on every fixture. So they decided to create a standalone ISI board that depends on the manufacturing of your PCB or the lot of those PCBs how they've been manufactured may differ. In order to always achieve the required calibration of the eye, you use different ISI traces to achieve your required calibration. So the methodology for the testing is pretty simple. You have a duty, and if it's a root complex, then you have to use the CLB compliance load boards. If you are an add-in card, you have to use CBB. You plug in your card. For root complex, you plug CLB. For the add-in card, you take the add-in card and plug in into CBB. The scope is connected to the transmitter side of whatever measurements you're going to do, and the scope will perform the measurements using PCI SIG tool for the back-end processing of the signal, and I'm talking about jitter and eye analysis. Next slide, please. So this one, as I already mentioned, this is in a large picture of the PCI SIG Gen 4 test fixtures. So CBB on top left, CLBs are on the top left, CBB compliance baseboard is on the top right, and in the bottom you have the ISI channel. Okay, next slide, please. So this one would be just a diagram representation of the connectivity and the required channels. So for the Gen 4, so for Gen 3, the channel loss, it's up to 20 dB. minus 20 dB loss. For Gen 4, the loss is minus 27 dB, and in Gen 5, it's minus 36 dB. So going in Gen 4 and Gen 5, if you are trying to go over the defined channel loss, you have to use retimers or redrivers. It depends on your application. But as you can see on the top form for the add-in cards, on the top diagram for the add-in cards, as I already mentioned, you have the CBB on the bottom and you have add-in card plugged in. And if it's a Gen 4, you have an ISI, standalone ISI board. But if it's a Gen 3, you don't have the ISI board. It's going to be just tested right there from the CBB itself. And you can see all of those defined losses, cable, ISI, the connector itself are all clearly defined by the card electromechanical specification. So the bottom diagram represents the root complex testing. So you have the motherboard on the bottom, you have the CLB plugged into the slot, PCI Express slot, and from there you obviously have to take the ref clock to the scope. So the difference between add-in card and root complex, for the root complex, you have to use a ref clock from the motherboard to be part of the testing waveform for the transmitter. And if you have the Gen 3, then that ISI, the standalone ISI is not present. But if you're Gen 4, the standalone ISI must be present to derive your compliance channel. And obviously for both the add-in card testing as well as the root complex, you do have a package loss that is embedded into the application for the testing. Next slide, please. Okay, so now this is just a little video that I will show you about the transmitter testing, how it's done. Please go ahead. So right here, we have just a typical Gen 3 transmitter testing setup, which consists of the CBB, riser card, CRU dot that we are using for the testing, and the add-in card that's plugged in to create a whole testing topology with the Oculus cable connected to the back end of that CRU SSD box. Okay. Okay, so right here we have the scope that's connected, and we are performing the measurements. So we actually invoke the application to do the measurements, and right now it's already actually at the 8 giga transfers per second testing, which requires different presets and the signal quality to be done and used. So by using the toggle button switch on the CBB board, I'm going through different data rates and the preset levels in Gen 3 in order to be able to do the testing. As you can see right now, we just went through all of the testing completely from beginning to the end for the transmitter Gen 1, Gen 2, and Gen 3. And right here it shows actually a Gen 3i. And we can look at the report. So at the end of the testing, you will get an HTML report that you can then save it as a PDF with every test that's been selected has tested. And right there, you can see the specification values and also the test values and a margin. Okay, so next slide, please. There should be a receiver testing. So right now we're going to go into the receiver testing as well as the receiver link EQ. Next slide, please. Okay, so what is the what are we trying to accomplish for the receiver testing? Well, we need to make sure that PCI Express has a link training mechanism that we need to double check and make sure that during the testing, starting from Gen 3, all of the testing gear that you use must be protocol aware. So for the receiver testing, it goes through the link equalization, which goes through the TS1, TS2. Those are training sets to train the link. And whenever the link is successfully trained, it goes through a recovery state within CTLE state machine to put the device under test into the loopback. So after that is achieved, and this is achieved with the optimized equalizers that are used for on the receiving side of the data under test. It goes into a loopback, and then the testing is performed It's a closed eye testing for Gen 3, Gen 4, Gen 5 going forward, and it all tested with the BR1E to the minus 12. Next slide, please. So right here, you can see this is a representation of the Gen 4 testing. So as you can see that the eye that we are trying to recover and calibrate it, the stressed receiver eye, is the eye height is an average of 15 millivolts, and the eye width is of about 18.5, 19 picoseconds wide. So the interesting fact is that for Gen 3, the eye height is actually 34 millivolts, and eye width is about 45 picoseconds. For Gen 4, I already mentioned it's a 15 millivolts, and it's about 19 picoseconds wide. And for Gen 5, the actually eye height stayed the same. It's still 15 millivolts, but the eye width has decreased to about 9.37 picoseconds. So as you can see, that as data transfer doubles, the eye height and the equalizations that are required to recover that eye is becoming more stringent and more complex. So you can see that when the eye is calibrated to a specific requirement by the specification, depends on the data transfer that you're testing, then we have to go through a link training. So the eye is closed and you're trying to go through that LTSSM state machine to train. So it goes through the training, and then you start performing the measurement. On the bottom, you can see that when the measurement is done, depends on the data rate, your test time will decrease. So for Gen 3, it's about 125 seconds test. For Gen 4, it's about 62 seconds test. And for Gen 5, I think it's going to be about 32 to 35 seconds test. But anyhow, when the testing is done, you are allowed to have only one error in Gen 3, Gen 4, or Gen 5. So that error is not correctable, but it is allowed to have one with the BR ratio of 1e to the minus 12. Next slide. So right here is going to be a short video where we're going to do a receiver compliance testing. Please go ahead. Okay, so in here we have a receiver setup test. As you can see, that riser card that will give you the 20 dB loss. This is a Gen 3, by the way. 20 dB loss going to the dot under test, which is plugged in with the Oculus cable going to this SSD of the CRU box. And a calibration was done with that CLB being present to calibrate the stress eye to the specification GNT transfer rate. So right here we have an application that is running on a bird, and we select and confirm that our calibration is complete and to the specification. So after we do the calibration and it's all done, we can actually select and test for receiver compliance, for receiver link EQ, testing on a long channel, and later we can do the transmitter link EQ testing as well. So after we invoke the application will give you a test setup that you can do. So there is a ref clock that's connected to the equipment under test. This is done for the purposes of bringing everything into the same clock domain. You can see that the receiver is going through the compliance channel, and you can see transmitter is coming back to test for the bit error rate. And power supply is connected as well. You can see that ATX power supply. So after we have this, we can actually confirm that our setup correlates to this picture. So it's right here, it's done, and we can actually do the testing. So we want to confirm that the board is configured for the external ref clock rather than internal ref clock. And we can start the test after confirmation is done. So after application is done configuring the test, the equipment under test, we can power on the whole board. It says power cycle, the GUT, and we can just energize the whole thing right there. and we can click OK. We want to make sure that everything is powered. Okay, it's loaded, and now we can click OK to perform the testing. So the testing has started. So the first thing you want to do is confirm that that rectangular box went to the blue color, which indicates that device was put into a loopback. And after all the stresses are applied, it will start doing the testing with the BR ratio. The dialog box will come up, which will tell you the required bits, the allowed errors, and also the status and number of errors that are encountered. You can see that the time it started originally with about 125 seconds, and now it's going forward for testing. Okay, so now we can look into the transmitter link EQ as well as the receiver link EQ testing. So this testing is done to confirm that when the test is done, or during in the field when the training is done, the host and devices will request different equalization settings that are required on a link. So when that's done, we want to confirm that everything works according to the spec. So in a receiver link EQ testing, that's very simple. So during the link training, some hosts like to work at different presets, and the device under test supposed to respond back with the equalization settings and make it to work. And for the transmitter, that's going to be a response time, because there is a defined response time that is required between the host and device. Next slide, please. So now we're going to go into a short video how the link equalization testing is done for the receiver and transmitter. So after receiver testing is done, we are going to power cycle the dot again and begin the receiver link EQ testing. So we want to confirm that all of the lights are on, and we can see the device went to a loopback. All of the stresses are applied, and the testing begins right now. So again, dialog box pops up, and the testing has started. You can see it's 125 seconds. So we kind of jumped the gun, and we can see that it's all completed. The receiver link EQ testing is done. Receiver link EQ testing is done at P7 and P8 presets for the Gen 3 specification. Now we can actually do transmitter link EQ testing. It's kind of it has a complex setup. So after selecting it, we can see that setup right here. We have to bring both the bird and a scope into the testing to make sure that when bird is requesting the duty under test for a specific preset, the response time is measured by the scope and confirms the testing. So now I'm verifying to make sure that my setup corresponds to the diagram presented by the application. We have both equipment in sync, and we can begin the testing. So the testing is ongoing. So right now the application is setting up the equipment, and now it says go ahead and power on the device under test. And after I do that, I confirm all of the lights are on and everything is good. I can push OK for the equipment to take over and begin the test. And it's pretty much the same. I'm kind of confirming on the scope that right now it's already actually doing P0 testing for the transmitter. As you can see that the bird requested to go into P0, the device responded back during the link training, and the scope captured that and analyzes. That goes through all of the presets from P0 to P9, and it actually corresponds with all of the measurements for the pre-shoot and the emphasis that are defined in a spec to indicate is it a pass or a fail. And then you can see everything is a pass, and that's your device under test. And the second one is the coefficients, which is represented in a second picture right now, where all of the coefficients defined in a specification, base specification of PCI Express for Gen 3, or if it's a Gen 4, then it's a Gen 4, that you can verify against it. So that pretty much concludes how we do the PCI express electrical testing on add-in card or root complex. So this one is the diagram of the testing itself, the block diagram. So you have the bird connected through the SI, and because it's a standalone SI, that would be Gen 4 going into Gen 5 as well. You have the board under test. It's a root complex or add-in card, depends on the topology you're after. You have a ref clock to bring everything into the same clock domain and for the testing. Next slide, please. And the response time for transmitter link EQ testing, as you can see, this one clearly shown as the add-in card type of a topology. You have a bird connected to the test fixture where the device under test is plugged in, and a scope as well. All of the signals are kind of split. It's a Y split where the measurements are done and correlated between both bird and the scope. That pretty much concludes all of the explanation how the PCI Express testing is done at JRL laboratory. So right now we can have probably a small session for Q&A.
Perfect. Fantastic. That was a great session, Eugene. Thanks very much. And thank you, Stuart, as well, for giving us a little show and tell from the CRU SHIP's platform component side. I do have a few questions that I'd like to relay on. I think I'll start with Eugene, though. You know, it's for those of us who are heads down and meshed in creating these devices and bringing them into the marketplace, one of the things that we sometimes skip over is stepping back and asking ourselves and relaying, why is it that we care about going through these certification processes? It looks like it's a lot of time, trouble, expense. What is the value of doing so?
The biggest value is to achieve interoperability with some other devices that you're not familiar with. So when the devices are released to a market, you want to make sure that it's flawless to the end user. It's plug and play type of scenario. You want everything to work. And that would be one of the ways to achieve it, is to go through the certification, because electrical, I only touched up on electrical portion of the testing, but there is also protocol testing that's involved, and also compliance to the configuration. Just a little history, when Gen 1 specification was first released, 2.5 giga transfers per second, a lot of people, when they created their configuration space, some of the unused bits in the register were don't touch. And during the design, some of the engineers decided, oh, I'm going to use it for my own engineering purposes. But when Gen 2 specification came out, it became to the point where those unused registers became used. And if the device wasn't properly designed, your whole motherboard was actually hanging during the boot because it couldn't figure out what it is and why it is. So that's one of the reasons. The main reasons is interoperability and compliance.
Okay, thank you. Cool. Let's see. We had a question come in about asking why this particular form factor instead of U.2. I will answer that from my marketing corner. So one, we have a device on the marketplace today called our QX318 or 318 that takes care of U.2 or our first iteration of M.2 form factors. So the main purpose, the primary purpose of bringing the SHIP's platform into the marketplace was, one, to develop a form factor that was as small as possible so that we could have a wider range of solutions built and delivered to ultimately the end users. Think about that. The form factor of the module that Stuart was holding up earlier, you know, you can easily envision that going into different use cases, much smaller use cases, you know, tactical edge devices, for example, that a larger form factor of a traditional storage media wouldn't be able to address. So, Stuart, I don't know if you want to comment on that yourself.
I would say that the U.2 form factor is much more bulky than is required in order to get pretty good storage. We have multiple terabytes in the cartridge at the moment. I mean, it's no problem at all finding a 2 terabyte device that size. The U.2 is first off, the connector is not reliable, and we'd still have to come up with some sort of a docking connector in order to make a removable product, which is one of the major goals of our products is removability. If you just need something that plugs in, then you can use a U.2. Sure. But if you need to remove it more than about 10 times, you really need to be looking at some sort of an interface. That's why, I mean, this is, you can see how the M.2 fits inside, because we have to mate the M.2, which has very low mate cycles, to the high mate connector.
Yeah, that's a perfect segue to another question that came in that is asking what the standard life of a standard connector is on an M.2 drive. I think I heard you say tens of cycles, but maybe do you want to elaborate on that?
It's the vendors don't really specify because it's a near zero insertion force device, and we've never actually tested it. But you can't just mate it directly in, right? It has to come in at an angle to get the zero force, and then it rotates down in order to mate it. And that action itself makes the volume that has to be accessible to the user quite large if you're going to actually utilize that.
Great, excellent point, excellent point. So let's see here, we've got a few more. So Eugene, you were talking about, I believe you said that the Gen 6 version of the specification either has been published or will be published shortly. Can you talk to what Gen products we're seeing in the marketplace today? I know you're working with vendors such as us that are testing future products, but perhaps you have a perspective on what we're seeing in the wild as we speak.
Yes, thank you, Chris. So Gen 6 is still in development. It hasn't been released, so there are no product on the market available today that runs at that speed. And remember, it's been switched from NRZ to PAM4 topology, so or modulation, I should say. So the spec right now, the base specification, it's still at 0.5 version, and it's only available to the PCI SIG members, those who are involved in developing the spec. So it's still very early on. But going back one generation, this is Gen 5, 32 gigatransfers per second. The base spec has been published already. It's at 1.0, and the CAM specification is at 0.9 and currently under review. So when everything is done and correlated, and we have fixtures ready and available for Gen 5, the CAM spec will go to 1.0 and will be released to the public. I think right now, we are looking at releasing this by the end of the year, but I can't really speak to it because it's not just my unilateral decision. It's actually the whole committee that looks to and decides to. But again, to Gen 6, it's still early on and there are no product available today.
Yeah, I know that we designed our chips platform for Gen 3 and Gen 4, and it feels like Gen 4, compatible host systems and so forth are still on the horizon. We're seeing Gen 3 most predominantly, but anyway.
Right. The connector between Gen 4 and Gen 5 is similar from the physical dimensions. The only difference is Gen 5 connector is surface mount versus Gen 4 in previous generation. It was a hole through type of a connectivity to PCB. Okay, great. And then a couple more quick questions for Eugene before we need to wrap it up. Someone is asking for embedded testing, can we use the DUT with the ASIC removed? What type of testing would that be? I mean, we can do signal integrity testing using vector analyzers for insertion and return loss type of measurements. But when the ASIC is removed, I'm not sure what that is after.
Okay. Okay, great. Thank you. And then can you explain more how the ISI board works?
So the ISI board for Gen 4, because it's a standalone ISI board, each trace introduce an additional half dB to its predecessor. So you can start with like 0.5 minus 0.5 dB with the trace 0, and trace 1 would be 1 dB loss. So all of those traces they're not highly tuned, but they're in approximate range of half dB increase from the previous one. So by connecting a setup, one knows what is the loss of the cables you're using and the CBB, CLB type of configuration loss. And you're saying that, okay, I probably need an additional 20 dB loss to create my own channel. So you start with the 20 dB loss and you start the application to calibrate your stressed eye for the receiver testing. And the application says, I cannot achieve, your eye is too open or too close. Well, if it's too open, it means you need to introduce more ISI. If it's too close, you need to reduce your ISI. And you just start going back by either one trace or two traces, depends how much you're trying to achieve. And at one point in time, you get to the proper ISI selection that will give you your calibrated stress eye, and successful calibration is complete. And you use that configuration to test your device.
Great, thank you. Well, again, thank you to you both for taking time out of your days to speak to these topics. Thanks to our audience for tuning in. And yes, indeed, we will be making recordings of this available. I believe we will be making the slide set available as you know. So stay tuned. If you are listening, then you had registered, and we'll make these materials available to you. So once again, thanks for tuning in, and enjoy the rest of your day or evening, depending on where you are.
Thank you, everybody.